All right, let's look at some algebra because we got a lot to go over today. My goodness, it's just a few things here, but there's a lot to it. It seems so. Good week for notes. All right, fifth hour. Fifth hour. Let's look at our grade screen just to keep up where we're at. So Sunday, you should have turned in the test. You should be done with module 2. So if you have anything missing from the first 2 modules, now's the time to get it turned in. Because we're now starting module 3. We're going to look at the greatest common factors and special products and factoring by grouping today. So if you haven't done factoring by grouping in a while, we'll get back into that. You may not have done much of it as it is, but I think you saw that some in Algebra 1. But we'll get back into factoring by grouping and greatest common factors. So let's take a look at those lessons today. We're in module 3. You can close that module 2 folder if you still have that open. Hopefully, if you got everything turned in. But let's look at the greatest common factors. Now, we're used to greatest common factors. I mean, we know factoring. Like when you factor 12, you can factor a 3 out of 12 and at least 4, or factor a 6 out of 12 and all kind of things like that. They start off with this little problem here where Taylor's at it again. She's trying to reframe a square photo with a square frame. But she wants to find the dimensions of the photo, see, because she's got some space between the frame and the photo. And so she could get a tape measure or a ruler, but, what's the fun in that? So her dad, who must be a math guy, said the area inside the frame is equal to this equation, x squared plus 12x plus 36. And x is the length of the photo. So she needs to know how much space is between the photo and the frame. How much longer is each side of the frame than the photo? So what is the length of the frame in terms of x? So they'll get to that. But greatest common factors. So when you were learning to simplify fractions, you had to do greatest common factors, right? So when you had 8 over 24, you had to find the largest number that would go into 8 and 24 that you could divide out of there, which in this case, 8 goes into both of those. So without getting the decimal, you could take 8 and divide it by 8 and 24 and divided by 8. And it is the same as 1/3. And that's legal to do because you're dividing by 8 over 8. 8 over 8 is 1. So you're dividing by 1. But you're just redoing it to where it's simplified. And it's a lot easier to understand. 8/24 is a little more complicated to 1/3. They're equal to each other, but it's easier to think about 1/3. All right, so they have an example here. I won't do this example since you have a video right here you can watch. In 2 minutes, it will factor 3w to the 4th plus 27w squared plus 15. But I'm going to do this one. It's a little bit more complicated. A little more complicated. So I'll do this one on paper. Let me write this down real quick. 6a to the 3rd, b to the 4th, plus 9a to the 6th, b to the 3rd,
Okay, so you would put, I think if I increase the
plus
pay,
20a to the 5th, b squared. And it wants us to factor that completely. And they're looking at all the factors of that. So let's switch over here.
the number of 6.
All right, so if we have this equation, 2 looks a little funny, and we need to factor this completely. So the greatest thing we do, the first thing we do on everything is the greatest common factor. Anytime we're factoring anything, that should always be step 1. Is there anything that we can pull out of each term? What's the greatest common factor? The common factor. They all have the same thing in common. Well, let's see what we have. We have a 6, a 9, and a 20. So 6 is 1 times 6. 9 is 1 times 9 or 3 times 3. So 1, 3, and 9 are the factors. 20 could be a 1, a 2, a 4, a 5, a 10, or 20. Any of those things.
own hypothesis. Out of predators.
10 or
that's
20.
really-
So what do they have in common? 6 also. Wait. 6 has 2 times 3.
As the length.
1 times 6, 2 times 3, 1 times 9, 3 times 3, 1 times 20, 2 times 10, 4 times 5. So is there anything in common? Well, this, but that doesn't help us. If we divide by 1, we end up with the same thing. These have a 3, but this one doesn't. These have a 2, this doesn't. But so there's nothing we can pull out as far as the numbers. But this has 6 times A times A times A times B times B. I'm writing it like that because that's A to the 3rd power, which is A times A times A, and B to the 4th power, B times B times B times B, plus 9, and this is A to the 6th power. So we got 6 A's. So I lower this down, maybe it won't bleach out so bad.
The last question here was, which part of these four
And then we have 3 B's.
and why? So there's 2 questions here.
And then the last one, we got 20, and we have 5 A's
That totally works. I like that. 'Cause you're clear.
being multiplied times each other, and 2 B's.
Make sure look at
So
yours. Make
while
sure-
these numbers, I could write this as 2 times 3 and 3 times 3 and 4 times 5, but since none of them factor out, it doesn't help anything. But when we look here, let's see, this has 3 A's being multiplied together. This has 3 A's being multiplied together, and this has 3 A's being multiplied together.
How?
So that means we can factor out A to the 3rd power.
Will affect the other organisms at first.
Yeah, make the A look like that. Maybe one of them fancy typing A's.
If I double my fraction,
A to the 3rd power. So we're taking A to the 3rd power out of each one of those.
what do you predict is going to happen to my graph?
All right. What else do we have? We have 4 B's, 3 B's, and 2 B's. So they all have 2 B's being multiplied times each other. So we can pull out a B squared because B times B is B squared.
Okay, so Tucker says decrease.
So those 2 would be canceled out because we've divided that out of each term. So now we can just take what's left. Let's see, we got a 6 and 2 B's, a 9 and 3 A's with a B, a 20 and 2 A's. So what's left when we factor this out? We're left with 6B squared. 6B squared, that's all that's left. Here we've got plus 9.
Tell me if I double my rapid
We have
population,
A to the 3rd power and B.
not going to change anything yet.
And then the last term, we have 20. All that's left is right there, A squared. So that is fully factored. That's pulling the greatest common factor out of there. That is taking the greatest common factor out of each one, and that's what's left. 6B squared plus 9A to the 3rd B plus 20A squared after pulling this out. You can always check that by multiplying this back in there. When you multiply 6B squared by A to the 3rd B to the 4th, you get 6A to the 3rd B to the 4th. So B squared times B squared is B to the 4th. A to the 3rd and 6. So you multiply it all back out and get the exact same thing you started with. So they look at it. Here's their 8 steps they go through. They looked at the factors of 6, 9, and 20 like we did, and the greatest common factor was a 1. There was nothing else in common. So since that doesn't change anything, dividing by 1, we leave that alone. And they did it with a factor tree. You can either do it with listing the factors, or you can do it with a factor tree. 2 times 3, or 3 times 3, or 4 times 5, which is 2 times 2, or any other factors in there. 2 times 5 would be 10, and, all that kind of stuff. But not one greater than 1. So then they looked at the 3 A's and the 4 B's, and the 6 A's and the 3 B's, just like we did, and factored out 3 A's and 2 B's, A to the 3rd B squared. And that, there it is, the way we had it written. a to the third b squared times what's left when we factor that out. Then they go in and they said these factors work because their product is the original. They checked it. Be sure to check it by multiplying it back together. So when they multiply it back together, they got the original equation left. So it says, okay, let's take a moment to compare the exponents to the original polynomials to the exponent of the factors. We started out with a to the third, b to the fourth, a to the sixth, b to the third, a to the fifth, b to the sixth. So look at this last one, a to the fifth, b squared. And we pulled out a to the third, b squared. So 5 minus 3 is a squared, 2 minus 2 is 1. So that's why that last term you end up with just an a squared. There's no b's left because we took out both b squareds. That just left basically a factor of 1. So when finding greatest common factors among the variables, look for the smallest exponent from each term and variable. Right? Even though there was a b to the fourth here, we couldn't take out a b to the fourth because the smallest one was a b squared. We couldn't take a b fourth out of the third term. So you have to look for the smallest one. The smallest one was a b squared. So that's what we pulled out. The smallest a was an a to the third. So that's what we pulled out. All right. Here's another example. 12 vw to the fourth, 28 v to the third, w to the sixth. So when you factor out, first with numbers, you have a 4, a 28, and a 12. You can do a factor tree if you like, but you can see that a 4 would go into all three of those. Because you got 2 times 2, 2 times 2 with the 4, 2 times 2. Every one of them has a 4. They all have two 2's in common, which 2 times 2 is 4. So you can pull a 4 out and leave a 3, a 7, and just a 1 on the last one. But then look at the variables. Right here, you got a v to the first. This has a v to the third. This has a v to the seventh. So we can only pull a v out because this one's only has just a v. So we're limited to that. With the w's, you've got w to the fourth. That's got to the sixth, and that's the eighth. So we can pull out a v and a w to the fourth. So they'll do that right here. They list it out like I had them on paper. And then pull out what you can. Just a v and a w to the fourth. And don't forget to check using the distributive property to multiply it back together and see that I got back the original polynomial. So it works. All right. So that's checking that. Factor this completely. Oh, this one's pretty good. Let's go ahead and work that together. They have it there that you can go through the steps. But we'll do it as a class here.
There we go. All right. Okay. So now it wants an observation of what happened.
So it says factor it completely. Okay. Well, it's an x squared. It's a quadratic equation. So we could just use the quadratic formula to find the solutions and the factors from that. But remember, step number 1, greatest common factor. I mean, this might factor as it is, but if we pull this out, it's going to make it a lot easier than dealing with these numbers. 2, 26, and 44. Those are all even numbers, so they should all divide by 2. So we pull 2 out. 2x squared divided by 2. Negative 26x divided by 2. And 44 divided by 2. Oh, this looks a lot easier to factor. When we just have an x squared, it's a lot easier than when we have a 2x squared. So we need to find the factors that multiply together to be 22 and add together to be negative 13. Multiply to be 22, they add to be negative 13, multiply to be 22. So 22, there's not many factors of 22. 1 times 22, 2 times 11. That's it. There's no other combination of numbers we can multiply to be that. And if it's going to be negative, when you add them together, one of those has to be negative. So the bigger one has to be negative. They both, but we want a positive number. So since we want a positive number, they both have to be negative because we want it to be a middle term that's negative. If this was a negative and this was a negative, that means we'd have to be multiplying a positive times a negative, and we want the bigger one. But since this is a positive, it has to be a negative times a negative to give a negative middle term. If we add those together, that's negative 23. If we add these together, negative 13. Hey, that's what we want. So the factors are negative 2 and negative 11. So this factors to x minus 2 and x minus 11. There it is, fully factored. So they want us to do fully factored. 2x minus 2, x minus 11. So they found the greatest common factor of 2. They didn't determine the binomial factors, right? Well, they did x and trying to figure out what goes with the x. So factors of 22 are 1 and 22, negative 1 and negative 22, 2 and 11, negative 2, negative 11. When you add them together, it's the negative 2 and 11. So x minus 2, x minus 11. That's what we had. Then checking it, multiplying those back together. They multiplied the two factors together before they multiplied the 2. They left the 2 outside. So you get back to the original polynomial. Okay, let's see what else they're doing here. Greatest common factors. Greatest common factors. And special product. All right, here's a special thing. Difference of squares binomial. Okay. This is going to be something that we got to look for. Okay, let's observe how these monomials are multiplied using the distributive property. So let's do these on paper just to see what they're trying to show us. G plus 9 times G minus 9. And then we're also doing 5G plus 8 and 5G minus 8. So what are they trying to show us? They're trying to show us a shortcut. I'll give you a spoiler alert. They're trying to show us a shortcut. But we got to figure out what in the world that they're showing us. All right, so if we multiply G plus 9 and G minus 9. Right, so we have to distribute. Right, we take the G times both terms. Then we take the 9 times both terms. G times G. G squared. G times negative 9. Negative 9G. Now let's distribute the 9 times G. 9G. And the 9 times the negative 9 is negative 81. Simplify this. G squared minus 9G plus 9G. Oh, wait, this cancels out, right? Negative 9G plus 9G minus 81. So we end up with G squared minus 81. All right, let's look at this one. 5G plus 8, 5G minus 8. Distribute the 5G first. 5G times 5G, 25G squared. 5G times negative 8, negative 40G. Now 8 times 5G is a positive 40G. 8 times negative 8, negative 64. Again, simplify. Again, these cancel out in the middle. 25G squared minus 64. Notice anything about those? We were multiplying 5G plus 8. I'm going to highlight the 5Gs, and we're multiplying G plus 9, G minus 9. And I'm going to highlight this.
Yeah, leave at least one hot.
Just to see if you kind of put the pieces together. So the first term was a G, and we ended up with G squared. That shouldn't surprise us, right? G times G is G squared. The first terms over here were 5G, and when we multiply 5G times 5G, you get 25G squared. Okay, that doesn't surprise us. But we don't have a middle term because those just ended up canceling out every time. But what do we have at the end? We have an 81. And what were the numbers on the end here? Nines. Those were eights, and we ended up with a 64. Well, 9 times 9 is 81. 8 times 8 is 64. I think there's something to this. Like, I know there's something to this. We had a plus and a minus, and that's what caused the middle terms to cancel out. But these are always a minus. Well, there's something called, let me write the name of this out here. The difference of squares. Difference of squares. What do you mean squares? This isn't a square, it's a number. Well, it's a perfect square, right? Because we can take the square root of 81 and it's 9. We can take the square root of 64, that's 8. So if you square something, you get its square. These are squares. This is a square because it's 5g squared, right? 5g squared. This is 8 squared. This is 9 squared. This is g squared. Every one of these are squares. And what's this mean? Difference. Well, difference is when you subtract. Right? When you add, you get a sum. When you subtract, you get a difference. So this is trying to teach us a shortcut. Trying to teach us a shortcut. If we can recognize we have this situation. Let me just write some problems down here. 4x squared minus 36. Let's do another one. Let's do 16x to the fourth minus 100. Let's do x squared minus 121. I just wrote 3 problems down. Can you tell me the 2 factors? Let me give you a hint. These are all squares. Would it be easier if I wrote it like this? X squared minus 11 squared. 2x squared minus 6 squared. 4x squared minus 10 squared. These are all the difference of squares. This is a square, this is a square, and I'm finding the difference when I subtract them. This is the square, this is the square, I'm finding the difference when I subtract them. This is a square, this is a square, I'm finding the difference when I subtract them. So that gives us a shortcut. If I know what the square is, 4x squared minus 36, that is 2x plus 6 times 2x minus 6. There's the factors. I just take the square roots. The square root of 4x squared is 2x. Square root of 36 is 6. Those are my numbers. Make one a positive, one a negative. Make one a positive, one a negative. 16x to the fourth. The square root is 4x squared. Because that's the square root of 16x. 4x squared. Squared. Square root of 100 is 10. Make one a plus, one a minus. That's the factors. Make one a plus, one a minus. This is a shortcut for factoring. Shortcut for factoring right here. This is a x
Balance our time this week.
times an x will give us x squared. That's 11 times 11. Make one a plus, one a minus. Make one plus, one a minus. With the difference of squares, if you recognize that you have a difference of squares, you can factor it very easily. X squared minus 11 squared. So that's x plus 11, x minus 11. Because that's x squared minus 11 squared. Because that's what 121 is. It's 11 squared. So it's x and 11, x and 11. This is a 4x squared and a 10 that are squared. 4x squared and a 10, 4x squared and a 10. This is a 2x and a 6, 2x and a 6, both being squared. 2x and a 6, 2x and a 6. One's plus, one's minus. Difference of squares. So this is one of the shortcuts that we're learning this week. If you recognize you have the difference of squares. So they're going to get into this and look at all the steps. So a binomial, here's the math terminology, a binomial where both terms are perfect squares and the terms are subtracted is called a difference of squares. Perfect square, perfect square, perfect square, perfect square, because it's a number squared. Perfect square, perfect square. Difference, difference, difference. Difference of squares. Here it is generically. A squared minus b squared is a plus b, a minus b. For whatever a and b is. In our situation, a was x and b was 11. A was 4x squared, b was 10. A was 2x, b was 6. Here's a list of commonly used perfect squares. Here's numbers that should trigger that thought immediately when you see these numbers. Seeing these numbers over here on the right, you should think, uh-oh, is this a difference of perfect squares? When I see 1, 4, 9, 16, 25, 36, 49, because this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way up to 12 squared. These are numbers, when you see those in an equation, you should automatically think, oh, is this a difference of squares situation? Is it a difference of squares? All right, so with that, I'm going to turn the chat on so you can participate here. Which of these are difference of squares and which of these are just expressions? Right? Like, let's look at this first one. 81 minus 25t squared. Is that a difference of squares or is that just an expression? This one, which one would I drop it under? 81 minus 25t squared. Difference. All right, so 81 is 9. 25t squared is 5t. 5t times 5t is 25t. So yes, this is a difference of squares. How about this next one? 64 plus 9r squared. 64 plus 9r squared. Ah, we fooled you. Is that a difference? That's a sum. That's a sum. That's a sum of squares. Yeah, that's not a difference of squares. That's a sum of squares. Yep. Fooled you. It has to be a difference. Has to be a subtraction. Has to be a subtraction. Okay, all the rest of these are subtractions. So there's no more fooling you in that one. This one's just, okay, is 9g squared minus 12? Is that a difference of squares? There's not a sum of square rule. It has to be an integer. A perfect square would be an integer. So, yeah, 12 is not a perfect square. We can take the square root of 12, but it's not a perfect square. Oh, can't see here. Some people struggle in seeing this because the Chromebook does it. Let's see if I can make it bigger on the screen. There, that should help. 9g squared minus 12. So yeah, 12 is not a perfect. This is a perfect square. 3g times 3g is 9g squared. But 12, it's the square root of 12 is not an integer. So that's just an expression. How about 4t squared minus 49s squared? Are those both perfect squares? Is this a difference of squares situation? Sean says, yep, that's a difference. It's a difference of squares. It's 2t and 7s, right? Because we'd have 2t plus 7s and 2t minus 7s. So, I put it in the wrong one by mistake. Yeah, you did say it's a difference. 16h squared and 1. So it'd be 4h and 1, 4h plus 1, 4h minus 1. Yeah, that's a difference of squares. And let's see, how about this one? Is that a difference of squares? Yep. So what is the square root of 16y squared? 4y. 4y. What's the square root of 4x? We'll do this real quick. So 4y times 4y. 4y times 4y is 4y. But if I put 2x, what's 2x times 2x? This is not squared. This is not a difference of squares because this is not a perfect square. Yeah, 2 times 2 works. So it's not this. Because if we multiply this back together, we'll get 16y squared minus 4x squared. That's what this equals. They got you there. There's no x squared. So this is not a difference of squares. Not a difference of squares. Just because you just have an x. So that's just an expression. Just an expression. All right. Bring it back down a bit so we can see what's on the next page. Here's another one, factoring. Oh, yeah, this was good because this uses the greatest common factor and everything. This kind of throws it together. So let's look at this. 3d to the 4th minus 363d squared. Whew. All right, so it's like, man, you want us to factor that? This looks like a booger to factor, right? Just saying right off here. We'll move this over here a little bit. But if we remember, our first step is always the greatest common factor. So this is 1 and 3. That's it. Is this divisible by 3? Oh, come on. Focus thing. There we go. Focus. 363. What are the factors of 363? 3 times 1, 21. That's 1 times 3, 2 times 3, 1 times 3. So this is 1 and 3. So they both have a 3 in it. So we can pull a 3 out front. We have a d to the 4th and d squared. Remember, we can pull the smallest one out of there, so we can pull a d squared out. So when we factor that out of the first term, that just leaves a d squared. When we factor out 3, that leaves 121 minus 121. This got factored out. So it's factored. It's not factored completely yet because now we have a difference of squares. Those are both squares. So that means we can factor this to d. And this is one of those magical numbers we're supposed to pay attention to. When we see 121, we should think, oh, wait, that's a perfect square. So it's a d plus 11, d minus 11 times 3d squared. There, that's the complete factorization. It's completely factored now. First, we pull out the greatest common factor. And then when we look at it, we're like, oh, now we've got a difference of squares. So we can factor that further. Now the difference of squares. So they got step 1, they pulled out the 3 and the d squared, and that left that step 2. That's a difference of squares. So they can factor to d plus 11d. And then they checked it here by multiplying them back together. And when they multiply them back together, you get back to the 3d to the 4th minus 363d squared. Let's see, 4d 6th minus 1. Is that a difference of squares? 4d to the 6th. Yeah, that would be 2d to the 3rd. Remember, d to the 3rd times d to the 3rd is d to the 6th. So this is a perfect square. And 1's a perfect square because it's 1 times 1. Factor the greatest common factor. There's nothing to factor out of there. So that's nothing. Factoring this, d to the 3rd times d to the 3rd. So that's 2d3 plus 1 and 2d3 minus 1. The d to the 3rd. That is a difference of squares. 4d6 minus 1 is 2d to the 3rd plus 1, 2d to the 3rd minus 1. And then they multiply it back just to prove that it all equals the right thing there. So, there we go. Back to the original 4d6 minus 1. All right, let's look at the next page. Perfect square trinomials. All right, so we're going to look at perfect square trinomials and see what expand square binomials. So let's see, what are we talking about a square binomial? All right, we're talking about taking a binomial and squaring it. So let's see if we can recognize anything here. So if we can recognize we have difference of squares, there's a shortcut. We know we can just take the 2 square roots with the plus and minus, and it's factored. Now it's trying to teach us something else. It's talking about a perfect square trinomial. So it says square binomials. So if we have x minus, let's say 5, and we square it, and over here we'll do 2 at the same time. X plus 3, and we'll square it. All right, so if we square these binomials, it will give us a perfect square trinomial. So let's do this. So this is the same as x minus 5 times x minus 5, because that's what it means to square something. And this is x plus 3 and x plus 3. So squaring it. So let's distribute x times x, x squared, x times negative 5, negative 5x. Now the second term, negative 5x, and negative 5 times negative 5 is plus 25. We can simplify that. X squared minus 10x plus 25. Okay, so taking this and squaring it gives us this. And we'll look at that and see if we notice a pattern. Let's do another one. X times x is x squared. X times 3 is 3x. 3 times x is 3x. 3 times 3. 9 like terms. X squared plus 6x plus 9. Are you seeing any patterns that can give you a shortcut to factoring? When you see this trinomial and know that this is the factors, and you see this trinomial and you know this is the factors, and then I'll just give you another one here. Go in the other direction. X squared, let's see how I want to do this, plus 14x plus 49. Can you tell me what the factors are? It's something squared. It's something squared. Looking at these two, x minus 5 squared gave us this. X plus 3 squared gave us this. So what squared would give us this? Just going to give you a minute to look at that, see if you recognize a pattern in that. John says 7. Kind of. I mean, we're not just going to put 7.
X plus 7.
X plus, yeah, and that's what Sean meant, I'm pretty sure. X plus 7. How'd you get that? Well, you get that because you know that whatever number is on the end is going to be squared. And whatever number in the middle is going to be double because there's two of them. We saw there was a -5 and a -5. We saw there's a 3 and a 3. So if you cut this in half, that should be the same number that you square. Take that middle term, cut it in half, and that should be what number is squared to be the end right there. Oh, that's a lovely shortcut. So we could go either direction. If we had x minus 10 squared, we know that's going to be x squared minus 20x plus 100 because we just double that, and that's the middle term. And we square it, and that's the last term. We doubled the 7 and made the 14x, and so there's another shortcut we've learned on perfect square trinomials. This is the perfect square trinomial because it's the square of this binomial. This is a perfect square trinomial. It's the square of this trinomial. So if you recognize, hey, look at that. If I cut that number in half and square it, it's that number. That tells you this is a perfect square trinomial. If I cut that in half and square it. So this is all about recognizing shortcuts. If I cut that in half and square it, it's going to be that. So we've learned a shortcut about difference of squares that we can instantly go to this. And we've learned about perfect square trinomials. If we recognize we have that, it'll cut straight to that. And if this was it would work even, well, with a 4 out there, it might create some problems with the thing. Right now, let's stick with this. X plus 7. All right. So they have several steps looking at that. Basically the same thing we just did. They're just using some different problems. So you can go through there and look at they like. But there's a pattern there. A squared plus 2ab plus b squared is a plus b squared. And in our case, the a was x and the b was 7. 2 times 7x, 14x. So looking at these, is this a perfect square trinomial or not? 6a squared minus 24a plus 12. When we look at that, if we cut 24 in half, that's 12. Well, it didn't squared, and we got this 3 out front. That's just certainly, everything's wrong with that one. Everything's wrong with that one. This one is kind of different because they got this big number with the r squared. Let's see, did they do any examples where something wasn't the r squared? I don't think so. Let's see, that should be, is that a perfect square? It is a perfect square because this is a 1, but 1 times 12. We may need to work one like that just to play with that. Because it went the other direction with the r squared. This one, if we cut the, is that a perfect square? It is. We need to play with that. All right, so 25g squared plus 70g plus 49. Okay, so things change a little bit when the first term, and that's let me just write that different paper. We're getting the background that's kind of making that look funny. Okay, so when this first term has a coefficient, it changes things just a little bit. Changes things a little bit. Because we look at this now and we're like, oh, well, if you cut 70 in half, that's 35, and 35 squared is not 49. What's going on here? What's going on here is we have a term out here. So if this is a perfect square, this would be 5g, right? Because 5 times 5 is 25. If you cut this in half, it's 35, but there's a 5 multiplying times it. So we're going to have to divide that 5 back out of it, and now it's 7. Oh, it's a 7. Does that work? Because when we multiply this back together, let's look at what happens here. 5g plus 7, 5g plus 7, since this is squared. 5g times 5g is 25g squared. The middle term would be 5g times 7, 35g, 7 times 5, 35g plus the 49. See, that 35 is made up of multiplying both of those together. So when you have a number out here, you're going to have to divide that back out to see if this is a perfect square. It gets a little trickier because on these other ones we were doing, well, this was just a 1. So it didn't change anything. 1 times 7. This is 1 times -5. So that's just -5. It changes that this number is not a 1. The coefficient's not a 1. It's still a perfect square trinomial, but we're dealing with an extra number that we got to divide back out if we want to figure this out. We have to take the middle term, cut it in half, and then divide it by the coefficient of the square root of this number, which would be 5. 5 times 5. And does that equal the last number squared? In this case, it does. So one extra little trick in there. Got divided by that. We basically had the same thing here, except when we cut that in half, at 7, we divide it by the coefficient of the first term, which was 1. So it's still 7. It didn't change anything. So we skipped that step. We didn't divide it by the coefficient of the square root of the first term. The square root of the first term, the square root of 1. But here we had to take the square root of 25 and divide it by that 5. Divide it by that 5 to figure out what the last term would be. Because remember, that middle term is made by multiplying those together. So this is a good one to check right here. 16p squared plus 72p minus 81. All right, let's see if that fits any of these patterns that we've looked at. So this would be 4p squared, right? 16p. So we know a 4p would be the first term if this works. If this is a perfect square, it'd be same times itself. So if we cut 72 in half, 36, divide it by the 4, 9. 9 squared is 81, but this is a negative 81. 9 squared is not negative 81. Because if we made this plus 9 plus 9, that would be a positive 81. So this says this is not a perfect square. The numbers are right. The numbers are right, but this would have to be a positive 81. Not a negative 81. So that negative 81 throws us off because 9 squared is not negative 81. So this one should fall in the non-perfect square. And it does. See this one? This is 11. That'd be a 5. So 110 divided in half is 55. Divide that by 11. That's 5. 5 squared is 25. It's all pluses. That should be a perfect square. This is not a perfect square, right? Because we take the 4 and we cut it in half, it's 2. Coefficients of 1 out here. 2 squared is not 16. All right. There's another one. More examples. It does walk you how to do that, so I won't go through all these examples because we only have so long in class. What? The IP? It just changed my lesson IP address. All right. We're reloading. Let's see if we can get it up here again. Okay. Reloading. When did it change my IP address? That's weird. All right. We go into page 3. 3. Okay, perfect square. Oh, that's where we were just at. We were on page 3. So let's go to page 4. All right, so this says we're going to take it a step further. Oh, this is looking at t to the 8th minus 81. That is a difference of squares because it's t to the 4th times t to the 4th and 9 times 9. So they're doing t to the 4th plus 9, t to the 4th minus 9. I think we already kind of took it to that step. Let's see here.
Hey, Tucker.
Oh, here's, yeah, okay, I see the step they're going. Now, here's what they're doing. Okay, let's do t to the 8th minus 81. I see the step they're going.
Yes, we used our time well, buddy.
It says fully factor this. Fully factor this. And we looked at it and we said, okay, yeah, this is a difference of squares because this is a square and this is a square. This is t to the 4th times t to the 4th. So that's t to the 4th squared. So this would factor to t to the 4th plus 9 and t to the 4th minus 9. It's like, all right, is that fully factored? Well, it's the factors of that, but if we're paying attention, what's this? That's the difference of squares. Oh, by golly, that is a difference of squares. So this one's fully factored because that's the sum of squares. But now this is t squared plus 3 and t squared minus 3 because that's the difference of squares. So now we got this. Wait, is this the difference of squares? No, 3 is not a perfect square. This is a square, but this one's not. So this is not a difference of squares. Only one of the terms is a square, just the t squared. But if this was a square again, we would take this another step. But so this is the fully factored. We have to combine what we're talking about. I mean, take it another step. See, oh, we've got a difference of squares inside a difference of squares. So don't stop there. It's not fully factored. You need to go one more step and do it again. And that's what they're doing with this one. They said, oh, wait a minute. We've got t to the 4th plus 9, and then t squared plus 3, t squared minus 3. So check and simplify. Check and simplify.
All right, questions before I turn you guys loose.
Okay, and so then we have another example here. This starts with a perfect square trinomial. So let's do that one together. D to the 4th minus 8d squared plus 16. Okay, so looking at that, this is a perfect square trinomial because if we take negative 8 and cut it in half, that's negative 4. And when we square negative 4, we get 16. So this factors to d squared minus 4 squared, which we can also write that as d squared minus 4 times d squared minus 4. Because that would be same thing as d squared minus 4. But wait, these are difference of squares. This perfect square trinomial factored to 2 difference of squares. So this is d plus 2, d minus 2, and so is this. This is the same thing. And so, well, I guess we should simplify this because look, we've got 2 of those and we've got 2 of those. So if we're writing this in the most simplest form, it's d minus 2 squared and d plus 2 squared. That's what that simplifies to. Because d minus 2 times d minus 2 and d plus 2 times d plus 2, d minus 2 squared, d plus 2 squared. Putting it all together. Our pencil's getting worn down already. So that's what they get to. Right there at the end. All right, that's the lesson summary. So we'll skip the rest of this. You got 4 pages of practice problems here. They want to make sure you understand it. Make sure you understand it. So here's several practice problems. That over there. Match one on the left. So, oh yeah, match this with its factored form. And this is just taking the greatest common factor out. There's no other factoring other than that. This is just taking the greatest common factor out. So which one of those match? If you say, well, that one matches that one. If I click them both, they disappear. Activity 2, factor each binomial, difference of squares. So what would the answer be? Difference of squares, right? So you do that, submit. Excellent. And then there's 4 problems there. So you can go through those. And then activity 3, factor each trinomial. Oh, that's a perfect square trinomial. So which one of those would that be? Submit. Excellent. And it's got 4 of those. Then you have another page over here. And another page after that. And another page after that. So you have several. So we're going to go to the next lesson. But just wanted to show you, there's 9 problems right there. 9 problems. So there is plenty of practice. You don't have to do them all. If you do several of these, and it's like, okay, I got it. I'm not having any trouble with it. Then maybe skip every, because they get harder. Some of them do. So you may want to skip towards one of the ones towards the end. And if I can do that, I'm in good shape. Oh yeah, look at that one. So you don't necessarily have to do all of them, but do enough to make sure you understand. All right, let's move on. Let's look at the lesson with this. The assignment with this. Factor that. Which of the following is a factor? Which one of these is a factor of that? One of the factors of this is, which one of those? Factor completely. We've got 10 questions, 10 multiple choice questions. What's the completely factored form of that? So, all right, let's see if it'll let me look at the next lesson.
The A and the E are on separate lines.
3.02, factoring by grouping. We're gonna look at that, and then we're gonna be done. This is taking a lot of time today. I understand. We ran into one of those days. All right. Let's talk about the discriminant real quick, because it tells us a lot when we're factoring quadratics. Something called the discriminant looks like this. Does that look familiar? You've seen that before. Because when we do the quadratic equation, where x equals negative b plus or minus the square root of b squared minus 4ac over 2a, the quadratic formula, well, there's that discriminant hidden right there underneath the square root. That is called the discriminant. I'll sharpen this. That's the discriminant. And the discriminant can tell us a whole lot. If we have an equation, such as, let's just do 2x squared minus 32. Oh, I don't want to do something that big. I'll do something smaller. Minus 3x plus 8. And we want to know, what kind of solutions does this have? Are these imaginary solutions? Are these actual integers? Is it fractions? What, irrational, irrational? If we check the discriminant, knowing that, ax squared plus bx plus c is that's how quadratic equations are written. B squared, in this case, is negative 3 squared minus 4 times a, which is 2, times c, which is 8. Negative 3 squared is 9, minus 4 times 2 is 8. 8 times 8, 64. Negative 55. The discriminant equals negative 55. That tells me the two solutions for this are imaginary.
First reminder I'm going to give you is that today is Tuesday. That means we have gray checks today.
And there's two solutions. They're both imaginary. So when you solve this with the quadratic equation, you'll end up with something, and I'm just guessing here. I mean, I'm not solving it. 3 plus or minus 6i over 4. Something like that. I mean, that would be your solutions. 3 plus 6i over 4 and 3 minus 6i over 4. That would be an example of two imaginary solutions. It's not going to be 1 and 6 or anything like that, because the discriminant was negative. The discriminant was negative. If the discriminant is positive and it's perfect square,
But our Google Classroom today, we are going to look again at that crumble zone, get some more
two
practice and help from that from last week.
rational solutions,
And work in power, we're going to do some notes on that first today.
which means the solutions are going to be integers or like 1/2. You know, it'll be something, it'll be like a fraction or two integers. So I'm going to put a big if right here.
So for tasks,
The discriminant.
one in. Okay. Remember that is from last
Discriminant. If the discriminant, if negative, 2 imaginary. If positive, perfect square, 2 rational. Positive, not square,
we're going to Nearpod. So on your Chromebook, go to join
2 irrational. 2 irrational solutions, which could be like 3 plus the square root of 7 over 4. See, that's not imaginary. That's a real number. 3 plus the square root of 7 over 4. That's a real number, but it's an irrational solution. And the other solution would be 3 minus the square root of 7 over 4. That would be your two solutions. If that was the first solution, that would be the second. So that's what it means if you have a positive that's not a square. If it is a square and the discriminant equals like 49, you know, when you take the square root of that, it's going to be 7, right? So if it's a perfect square, you have two rational solutions. Other cases, if it's 0, one solution. If the discriminant is 0, you just have one solution. So there's the 4 things the discriminant will tell you. Discriminant, if negative, if positive, perfect square, if positive, not a square, 0. So that's what they want us to pay attention to when factoring a quadratic, is that the discriminant tells us a lot, that b squared minus 4ac. And that's what this paragraph's talking about, the roots, the discriminant.
Dylan.
So looking at a perfect square trinomial, like x squared plus 8x plus 16, that's a perfect square trinomial. If we took the discriminant, that would equal 0. Because there's only one solution. It's x plus 4 squared, so the solution is -4. There's only one unique solution on any perfect square trinomial. That's always going to be the case with a perfect square trinomial. All right, let's look at page 2. We're running out of time here. Factoring by grouping. So we need to look at factoring by grouping. And they start and go the other direction. So I see group 1, group. Let's look at group 2. All right, we're gonna do some samples, and then you guys, you can go back and look through these examples in the book because they've got those laid out for you. All of that good stuff there. Let's see. I think it's like false primes. Factoring trinomials by grouping. We'll do some of these on paper so you can see exactly what they're doing there. I'm trying to see how far this lesson goes. Page 6 was the last page of the lesson. Again, they're checking that discriminant that we just talked about.
There we go. Enter that code, NNB.
Lesson summary. So here's our lesson summary. I'm going to do some more examples to show you that. Checking the discriminant. If it's 0, if it's a positive perfect square, positive but not a perfect square, negative. Steps for factoring. So here's steps for factoring. We're going to go through this right here. Steps for factoring polynomials with 4 terms. And the steps for factoring trinomials by grouping. So we're going to do it with trinomials by grouping because that will basically give us the 4 term. So let's see what examples they got here that we can just pull one of these to do.
We've done before. So
that one's already 4 terms. Here's one. All right, I'm going to write this. 2b squared plus 7b plus 3. All right. Looks too much like a 6. B. All right. B. Those are B's. All right. So if we're going to factor this by grouping, what we're going to do is we're looking at rewriting this. We're looking at rewriting this to where we're going to change the 7 to something else that we can use for grouping. So what we're going to do is we look at first the coefficient of the first term and the last term and multiply those together. 6. Okay. 2 times 3 equals 6. So we need the factors of 6 that would add up to 7. 1 times 6 and 2 times 3. Right? That's the factors of 6. Well, this, when we add these together, be 7. So we're going to change this to 2b squared. We're not changing that. We're just changing this to be plus b plus 6b plus 3. These are exactly the same equation. The only difference is I've taken the 7b and made it a 1b and a 6b. A 1b and a 6b. So now I can group these together. Take the first 2 terms and the second 2 terms. So looking at the first 2 terms, what can we factor out of that? 2b squared plus b. Well, the only thing both those terms have in common is a b. So we'll pull the b out, which leaves 2b plus 1. Right? So if we multiply b back into there, it'd be 2b squared plus b. Now, what can we factor out of this one? 6b plus 3. Greatest common factor would be a 3. So if we factor 3, 6b divided by 3 is 2b. 3 divided by 3 is 1. Okay, so now I have 2 terms. I have this term, b times 2b plus 1, and I have 3 2b plus 1s. Oh, look, both of these terms have this in it. I can factor that out. 2b plus 1. So when I factor it out of here, all I have left is a b. When I factor it out of here, all I have left is a plus 3. So this is the factors of that. That's as simplified as we can get. Now you have choices. I could have done that. Let me just one more time over here. I could have done that a little differently because I chose to write 1b and 6b. I could have chosen, let's see how this changes it. I could have put the 6b first. That would change things, right? See, 1 plus 6 or 6 plus 1, that's the same. I'm still writing the exact same equation. I've just rearranged the terms. But now it's different when I group it. I've grouped it differently. I've grouped it differently. So now when I look at this one, 2b squared plus 6b. What can I pull out of there? Well, there's a 2 in both of those. And there's a b in both of those. What's left? 2b squared divided by 2b leaves just a b. 6b divided by 2b leaves just a 3. So what can I factor out of here? I've got plus b plus 3. There's really nothing. I can just factor a 1 out, and I would still leave a b plus 3. I'm trying to make these the same. That's why I've just factored 1 out to leave it the same, because now I want to factor b plus 3 out of both terms. So what's left here? Just 2b. What's left here when I factor b plus 3 out? Just plus 1. And look, I got the same answer. They're just written the other way, which is fine. Yes, Bethany.
What happened? Where did the 7 go?
I made it a 6 plus 1.
Oh, right. Yeah, that makes sense.
Yeah, 6 plus 1. 6, I'll write the 1b. 6b plus 1b. So I didn't change it. I just rewrote it. You agree? 6b plus 1b is the same as 7b. So yeah, that's what I did up here too. I just wrote 1b plus 6b. I just rewrote it because I looked at the 6 times 3. I mean, 2 times 3. And I said, what factors of 6 would equal that middle term? 1 and 6. So I said, okay, I'm going to make the 7 a 1 and a 6 instead, so I can group them. So by grouping, we can factor that. That's probably easier than trying to factor that by itself. I know it's a quadratic. We could use the quadratic equation, and that still would have been kind of a mess because we end up with something funny because of that 2 out front kind of creates problems. Let's look at another one. Let's pull another example so we can look at that. But yeah, we're just rewriting it. Let's see. Oh, we just worked this one. What is the answer? 2b plus 1. That's the answer. We just worked that one. So we can get a better. Oh, this will be a good one. 6w squared minus 40w plus 66. Ooh, that's a good one. All right. So again, the first thing we want to look at is greatest common factor. Can I pull something out to make that simpler? Because that's some pretty funky numbers. Let's see. 6 is 2 times 3. I don't care about the 1 times 6 because factoring a 1 out, then, or a 6. But 6 does not go into 40. So 40, let's see, what can we do? We can do 2 times 20. 3 won't go into it either. So 2 is really the only number I can pull out of that. So let's pull out a 2. So I have 3w squared minus 20w plus 33. Okay. So that's helped a little bit. We pulled a 2 out because everything can have a 2 out of it. There's no w in the last term. This is not going to have a 3. 2 times 3 is really all I got here is 6. 6 and 3 doesn't go in there. 2 is the only thing that's going to come out. So now I'm going to ignore the 2 for now. I know it's still out there, but I'm trying to factor this. So I take the 3 times the 33. And that's 99. Ooh, what are the factors of 99? Well, 1 and 99. Now this is the positive. This is a negative. So these would both be negatives. Let's see what else. 9 times 11. Oh, that equals 20. When I add those together, this is 100. But when I add this together, that's 20. So I can rewrite this like this. 2 times 3w squared. And instead of 20, I'm going to make it a minus 9 and a minus 11w plus 33. Okay. Same equation. All I did is took this negative 20 and made it a negative 9 and a negative 11. So instead of negative 20w, I broke it out. And I did that so I can group them. Still have the 2 out there. 3w squared minus 9w. I can factor out a 3w, which leaves w minus 3. Right? When I factor a 3w out of it, 3w squared divided by 3w is just w. Negative 9w divided by 3w is just negative 3. Now, what can I factor out of here? Looks like, now again, so I can factor out 11. If I factor out 11, that leaves negative w plus 33. But notice, not 33 plus 3, I'm sorry. Plus 3, because I factored 11 out of it. But I want these to be the same. Those are not the same. I'm purposely trying to make those the same. So instead of factoring out 11, I'm going to factor out negative 11. So if I factor out negative 11, this becomes a positive. So that's just w.
Force times distance. What was the force?
And negative 11 out of 33 is negative 3. Now I've purposely made those the same.
10. Yes.
So I can factor this out now. So I've got 2 times w minus 3. And when I took w minus 3 out of this, I just left 3w. And when I factor it out of here, it leaves negative 11. So there is the fully factored. Got a parenthesis. That's the fully factored version of this. Now, again, you think, now, what if you did that differently? You can do it either way. Just choose the one that's easier for you. Oh, I need to go to this one. 3w squared minus 20w plus 33. If I would have switched these, because it doesn't matter which order I put those in, it just may make it easier. Let's put the 11 first this time. And then the negative 9w plus 33. I want to put those, whichever would be easier after I group it. See, 3 and 11 don't have anything in common. But 9 and 33 do. They have 3 in common. It may be that nothing's in common, but if I switch them, then it would be. This works real nice because 11 and 33 and 3 and 9 both factor. Now, the only thing that factors out of that's just a w. 3 and 11 have nothing in common. And when I take w out, I got 3w minus 11. But what factors out of here is a negative 3. And that leaves 3w minus 11. So when I factor 3w minus 11 out of both of those, that leaves w minus 3. I still get the same answer at the end, w minus 3 and 3w minus 11 times 2. But it just may be easier to group them the other way. Again, your choice. It'll work either way. But you're just trying to rewrite this to where you can group them and factor them. Because looking at this, it's like, my goodness, I don't know what the factors of that are. Well, let's group it and factor it this way. And now those come out real nicely. All right.
What should that answer have been?
That is it. We're not going to go through anymore. You can go through. There's more practice. There's more examples in here. So if you're still struggling with that, we didn't do enough in class to help you understand that. Go back and look at the extra. There's lots of examples in there. So that's good. That's why I took all the time I wanted to take and more, but there is still lots of examples in there that you can go back through. And if you don't understand them, come see me. This is an A-Day Friday, so we'll only have class on Thursday. So if your grade's below 70, I'll expect to see you. But even if it's not, and you're struggling with this, you're trying to do these assignments, and you go, gosh, I'm still not getting this factoring by grouping thing. Come see me. We'll work on some together in class on Thursday. Or you can email me. We can set up a time, whatever works best for you. But yeah, try and do that. See what you can do to, work on this before Thursday's class so you know if you need help. That's a good idea. At least try it. Okay, guys. I'm tired. That's plenty. That's plenty. We'll see you guys next time.